All right, and we're back. This is 4.NET Conf, and we're ready for our next speaker, Henry Bain. Henry is an independent software architect and developer. His interest is the cloud, agile and DevOps, and he likes to implement testable and maintainable software, so we're really eager to see something of that. He's a conference speaker, and he's actually awarded the Microsoft MVP Award in 2019 and in 2020. And he wrote a book, Implementing Azure DevOps Solutions. So, hey Henry, how is life on Texel?
Hey Eduard, life is actually very, very good. For the first time in a couple of days, we have sun outside, with me being stuck inside, but still sun outside.
Yep, we're stuck inside, so I believe all the rules and regulations are the same on Texel. You have to stay home at 9 from as of tomorrow. Nothing to do about that. So can you give us a brief introduction of what you're going to tell us in the upcoming hour?
Yeah, sure. Let me try to tell you a little bit without spilling too much of the beans. Well, as you know, I've been working for quite a while at a big company where we've built a distributed system. I think you're still working there as we speak, so you're probably intimately familiar with what I'm going to be talking about.
Is it?
But of course, when you start building such a thing, especially in microservices architecture, there are a lot of things that you learn when it comes to testing and monitoring that application. And I think that the core of this talk is the stuff that I have learned while going on that journey. And I think we have all seen the flashy presentations of how to use Azure Functions, click, click, boom, and it's done. And we've seen CosmosDB, click, 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 next, next, finish. And we have a distributed database, cloud native, distributed all around the world. It's amazing, it's cool. But what happens when you start building applications on top of those things? How do you test them and how do you monitor everything is working? And that's going to be the topic of today's talk.
All right. I'm really eager to learn everything. So I'd say the floor is yours. Take it away.
All right. Thank you. So hi everyone. Unfortunately, from my own working room on Texel, where the sun is shining, I was really looking forward to my first hybrid conference. But as most of you, we're gonna comply with the regulations, so I'm working still from home. Hey, I'm going to be talking to you about my personal journey of learnings on testing and monitoring distributed applications that we build using Azure Functions, CosmosDB, and Azure Service Bus. But reflecting on the title, I think the real topic of the talk is going to be quality. How do we make sure that the things that we deploy are of high quality? And how do we know that we find out as soon as something is not working as we want it to work? So how do we get less very big explosions? And how do we get more smooth running systems? My name is Henry Bain. Eduard already said I'm an independent DevOps and Azure architect. I live on Texel, which is in these times a great benefit, for which I'm very grateful. If you have any questions, you can find me on Twitter or LinkedIn, or even old-fashioned email. But feel free to post your questions in the chat or on Twitter. And if a question comes by, Eduard might even interrupt me to get your question answered. Hey, in this talk, I want to start with a little bit of a story. I think it's about 2 years ago that I was tasked with building a distributed system. We came together, 2 architects, and we thought about what to build. I think it took us an afternoon, and then I started building the thing. It was one centralized transaction engine. On top of that engine, a bootstrapping component that got some initial data in there. Next to that, we had a third component that initiated transactions on our engine. And finally, we had a number of downstream agents that were responsible for executing those transactions in underlying systems. Very abstract, so maybe a picture might help. Something like this. Transaction engine at the core, 2 inputs, and later on, a lot of more transaction agents that we initiated transactions upon. Now, when I started building that thing, it took me only 3 weeks to build a proof of concept. From there on, it took another engineer and myself 3 months to build the first iteration of that system. But from there, things, rapidly went south. A year later, we had a total of 6 full-time employees to run and further develop that system in parallel. So we were already providing service to a number of customers, and we were improving on the system at the same time. And I think that this really shows that things like CosmosDB and Azure Functions deliver on their promise. We can very quickly get solutions up and running. But there is also the risk that if we don't do it the right way, we don't invest enough in quality, they can really slow us down later on in the project as well. And that's my learning, and I want to try and share with you what we have done to work on quality alongside with developing features. This is a quote that came up when I reflected on this with one of my fellow peers in the project. Good decisions come from experience, but experience comes from making bad decisions. It's a quote by Mark Twain that you see lying around on the internet quite often. But there's also a second part to this quote, which is also very interesting. You know, this is life. It happens, so never regret it. Just learn from mistakes and go on. Now, in my personal case, I regret nothing. I learned a lot, and the learnings also helped us to improve upon the quality and the continuous testing and monitoring of our system. Now, before we dive into that, I think one of the primary learnings that I had was that building distributed systems and having them of high quality and working very, very well is very, very hard. So my first advice is do not build distributed systems if you don't have to. I know that we're all, liking microservices. It is hip, it is cool, it is new, and it clearly has benefits under certain circumstances, but it's not the solution for every single problem. Definitely not. Because distributed systems, they come with disadvantages. And the first one is that building those things requires a different skill and mindset. If you are working in a team of developers that has been developing monoliths for 20 years, and all of a sudden you decide to move to a microservices architecture, that's not very easy. There is new things you need to learn, and there is a new way of working that you need to adopt, because otherwise you're not going to succeed. The second problem is that communication is complex. If you are building a lot of components that have to work together, all those components have to communicate. But most likely, different teams or different people are going to work on different components. That also means that all those components not only have to communicate, but also the people have to communicate about their components. And that takes a lot of overhead, takes a lot of times, and mistakes might happen there. Thirdly, more components, more costs. I think as a general rule, you can say that having one big monolith that completely utilizes 3 VMs is going to be cheaper to run than a system that is distributed over 20 runtimes. You're going to have spare capacity in all places. There is more to monitor, there's more to deploy, etc., etc. Now, maybe when you really move to serverless and only serverless, this doesn't hold anymore. But if you're using old-fashioned deployment platforms, you might definitely have more runtime costs. Finally, like I said, testing, monitoring, and troubleshooting this stuff is actually very hard. But that being said, we still build distributed systems. Why do we do that if it's not easy? Or not necessarily, at least better than we used to do. There are a number of reasons. First of all, there is less impact of errors. Let's say that I have a very complex distributed system, and one of the components is a fulfillment service. If that service goes down, and the remainder of the system as a whole is correctly engineered, everything else will correctly keep working, and once the fulfillment system is up again, it will start processing its backlog of items to ship. So we can lessen the impact of mistakes or bugs or temporary unavailability when using properly built microservices. Another reason is the focus for developers. If we have a monolith, and I've worked on monoliths close to 10 million lines of code, including lines with thousands of characters, it is very, very hard to understand that system as a whole. You as a developer might need years to understand how different parts of that monolith work together. And even after 20 years, sometimes you still don't know what a certain package does in relation to the system as a whole. Having multiple smaller systems allows people to really focus on the systems that they work with every day and to really understand them. And especially in this context of people shifting projects and companies faster and faster, it also helps you to more quickly be able to understand the system that you're working on before it is time to move on to another job. Thirdly, the need for speed. Our world is changing. We don't have years anymore to develop new projects. When an idea comes up, we really want to go to production maybe the same day or at least the same week. Well, if you have smaller systems, it is easier to incorporate change. They compile faster, Visual Studio opens faster, they are quicker to understand. Everything is just faster for a smaller system. Systems also deploy faster. If you compare a deployment pipeline for a very large monolith with the deployment pipeline of just a microservice, you can be amazed at the difference in deployment time. Teams learn and develop faster. We've talked about that a bit already. Finally, and maybe this is not really pleasant to hear, but it's just the truth. Smaller components can also very easily be replaced. If an implementation is just really, really bad, you take it out and you put in a replacement. Or if you just want to stop with fulfillment altogether, you just remove the microservice and the two systems calling into it. However, in my personal opinion, I think the really big driver for microservices, distributed systems, is that large organizations are complex. And thus inherently they need complex systems to work. So going back to the example that I introduced at the start, the transaction engine that we had to build as a team. If we zoom in on that, this is not something that we as a team build. This is actually something that we as a company as a whole build. Actually, that transaction engine and the first transaction agent were implemented by the team that I was part of. The bootstrapping component I mentioned was not developed by us. It was developed by another team, a team that was part of the same department. They were on a group of desks across the aisle. We could walk up and down to them. They were very friendly, very helpful. And sometimes when you ask something on Wednesday, they say, sure, we're going to help you, but it's going to be Monday because we have our own priorities. Well, we were thinking Monday, we need this today. All of a sudden, you have a team boundary between the two of you. And even though everybody's helpful and friendly, things are going to slow down. Moving on. That user interface that I talked about, the transaction initiation component, was not really a component of itself. It was just a set of widgets that were hosted in another application. I don't know, maybe you know about, for example, Dynamics widgets that you can build and host in like a container. They were built by our team, but they were deployed by another team, the same team as the bootstrap component owned. Still very friendly, helpful, but you can imagine the problems that come with us building something and them deploying it. I think we have a traditional problem here now. But looking forward to the other side, the system that we had to perform some of the operations that were part of the transactions on was managed by yet another team. Still close by, but here we have a second team boundary. And looking further and further, the problem just gets worse and worse. The second transaction agent that we joined was operated by a team that was still part of the same department, but was in another country. We've been there for 2 days, and then we had to work together for a year without ever seeing each other. And then there was finally another team that we actually never met, but they also connected to our transaction engine, and you can imagine that that was even harder to cooperate. Now, this is one of the big drivers for distributed systems, I believe. We don't want it to work all together in one large code base that we all fiddled in. We all wanted to have our own component, and we needed ways to interact with each other. And this was a driver for microservice architecture, with each component aligned with a different team. So, looking back at the journey, concluding that it's maybe not always the best way to build a microservice architecture, but still sometimes we're forced to. How do we test those systems? Well, I think we have to start at the basics. Let's start by taking a look at how to test the individual components. And that's really important because if you have a monolith, you can have the whole thing running on your own system, and you can run end-to-end flows against that system on your local computer when you've made a change before publishing this change. When you're building a microservice architecture, it is almost always impossible to have everything running on your own system. So you cannot run end-to-end tests. You really have to think about which requirements does my component have, and am I really fulfilling them? And you have to verify that over and over again. So you really have to start automating tests. Microservices without automated tests, I think that's going to be a tough ride. Reason about which types of tests we need, and there are two models that I want to introduce you to. On the right, we have what is called a testing pyramid, and on the left, we have what is called the icicone of tests. And here we see 4 different types of tests: unit tests, integration tests, and system tests, which we consider automated tests. And on top of that, we have manual functional tests to test if everything is working together. Now, in my definition, a unit test is a class that tests another class. An integration test is a class that tests the integration between at least 2 other classes or an external component. A system test, and these 2 tests, integration tests and unit tests, they never run against the deployed system. They instantiate components of that system in isolation in the test and then destruct them after the test. For me, system tests are tests that run against the deployed system as a whole. And these tests can catch errors that we cannot catch with integration tests and unit tests. Maybe errors in the configuration, errors in the dependency injection configuration, things that we cannot find by testing parts in isolation. And on top of that, maybe there are some manual functional tests that we want to run to make sure that everything is running end to end. Now, the question that always pops up after introducing that pyramid, which says that we want to have a lot of unit tests, fewer integration tests, even fewer system tests, and maybe just 1 or 2 manual tests. The question is up, how many do I need of each? So my recommendations are these. First of all, unit test everything you can. If there is a requirement embedded in your component, try to put it on the unit test. And that's a very, very absolute statement, but I have found that that really works. Then write integration tests for every time that one of your classes integrates with another component. So that's another component at the architectural level, not. But that integration test should only verify your assumptions about how that other component works, and they should be as atomic and as small scoped as possible. So try not to get business requirements leaked into that integration test. Things like retry, things like formatting or encoding, try to leave them out of integration tests if possible. And then system tests, from my point of view, they are a necessary evil. Integration tests and unit tests, they are quick to run, relatively quick to write, and they provide very fast feedback. And often you can execute them from your local computer against something running on your local computer. System tests cannot. We just really need them to remove some of the final risks of that remain after running integration tests and unit tests. And to answer the question, what I've seen in practice is that a ratio of 1 to 5, maybe 1 to 15, and anything in between for every level often works. Or in bigger systems, I can have tens of thousands or thousands of unit tests, hundreds of integration tests, a few system tests, and hopefully 0 manual tests. But that's a personal take, and your mileage may vary. Now, reviewing those different types of tests, I think that we're all familiar with unit tests, so let's skip those. And quickly move forward to integration tests. Now, there are a lot of different interpretations for integration tests, but I think the bottom line is always that they should be about, the integration between 2 parts. But I try to focus on where one part of my system integrates with something outside of my system. So not on integrating multiple parts of my system. But that's a choice. Now, if we take our system on the left, we have a number of classes there, 3 of them. And class D calls into the REST API that is part of another system. Now, in my system, class A and class C, I can put on the unit test, and I can make very, very sure that there are no bugs in those implementations using unit tests. Or at least I can build a very high confidence. But I cannot do that for class D. Class D cannot be tested in isolation because it makes outgoing calls. So for me, this is a scope for integration testing. Is class D correctly interacting with the REST API? Now, to make the amount of integration testing effort as low as possible, we should try to have class D focus only reflect the API capabilities of that external system within our own system, and not let any business logic slip into the implementation of that class. And if we do that, we can write integration tests in a way that is very, very similar to unit tests. For example, in this case, I'm instantiating class D. Now, class D needs to call an external system, so it's going to need credentials of some kind. And from there on forward, I can just make the API call that I need, create the user, and then assert that I can find it again. Now, in here, I think comes a very controversial statement. What I try to do is I make my integration tests connect to the production environment of the other component. And the reason for this is that I really want to make sure that my class D interacts correctly with their production environment when it is deployed into production. And no matter which kind of system, no matter which kind of approach I choose, production is always going to be the most representative of production. But this relies on the assumption that in the system that I'm calling into, I can get some kind of namespace or scope or container within which they allow me to securely execute my tests without interfering with their day-to-day operations. Let me give an example. For example, if the system that I'm integrating with is Azure, or is just a regular Active Directory, maybe they can create an organizational unit that I can get access to execute my integration tests. Or when I am executing integration tests against Azure DevOps, maybe I can get an organization or a project that's just dedicated to my tests. Or when using CosmosDB, maybe I can get a CosmosDB database that's just dedicated to me executing tests. And I have a scope that I can use and doesn't interfere with their production and business. Now, another argument that may give against this is that, hey, if you are testing against our production environment, maybe you can make our production environment unstable using your tests. But if you reason about it, isn't that kind of a weird statement? They believe that their production environment might be so brittle that a few of my tests can break it. What about bad actors all in the world? If you treat production as it is brittle and breakable and not worth of testing against, trust me, it will not be worth testing against. It will not be a very robust system. So very controversial, but I think there is value from this kind of testing. It's not always possible. So as an alternative, you might try to set up and destroy a new environment for every single test case. But of course, that's going to be more expensive. Unit tests out of the way, integration tests out of the way. Let's take a look at system tests. The necessary evil, especially needed to verify configuration. So here I have a sample architecture. Our system is in the middle, and everything is initiated by another system on the left. Then there is a system on the right that we call into at the completion of our operation. And finally, we have a pub/sub system going on in the middle of our system, which is connected using a queue on the service bus namespace. Now, what I want to do with a system test is I want to have a testing scope that is as wide as possible. I really want to start outside my system, and I really want to end outside of my system. But actually, when you take that requirement into mind, there are two flows. One starts in another system on the left and ends in the service bus queue, which is outside of my system. And the other one starts in the queue and ends in the other system. So actually, I think there are two cases for a system test here in this architecture. So let's focus first on the left. What I do, I take the other system out of the picture, and I drive the test from my test case, and I call into my deployed system. And then the thing that I want to check, the thing that I want to sense, is that if I get a correct message on the queue. So this is, I think, a good test scope for the part on the left. Switching focus to the right, what I want to do, I want to take that out of the other system. I want to sense from my test if that system is being called properly. And I want to drive the test by putting a message directly on the queue. Now there is a bit of a problem going on here, and that's on the right. in my experience, when you're calling another system using HTTPS, it can be a bit tricky to sense if that system is being called directly, because it is outside of your control. Maybe they generate very good logs that you can check to see if the call has been made with all the right parameters and the right content, etc. But what I have done in our systems is that we actually replace the implementation that should call their system with an implementation that puts the output directly back to the test. So we cheated a little bit on this one. Now, I think that's a lot of talk and a lot of slides. So maybe it is interesting to see how I apply these thoughts into a demo application. Unless there are any questions maybe at this point. I look to my left and I see
no, we don't have any questions yet.
People probably zoned out, but I'm just going to try and win them back. Hey, I have created a small system for managing the legendary to-dos. So this is an ASP.NET application, and it is an API. It has a to-dos controller, and it implements operations for adding a to-do, deleting a to-do, retrieving to-dos, and updating a to-do. Now, this controller relays all the actions into a to-do service, which does the actual implementation of the operation. For example, the creation of the to-do, the updating of the to-do. Now, this service gets injected a logger, because we want to log everything, but it also gets injected a to-do repository. And that repository is an implementation of the repository pattern that I use for storing and retrieving things out of the database. In this case, a CosmosDB database. So looking at that repository, what it does, in its constructor, it gets a configuration on how to connect to CosmosDB, which is a Cosmos locator URL, a password, a database name, and a collection name. Those four properties. And using those properties, I can implement interactions with CosmosDB, which are very much in line with, there, I fixed it, very much in line with the recommendations on how to use that API. Nothing very, very new, I hope, for people familiar with Cosmos. Now let's take a look at how I test the different things going on here. First of all, when I look at the to-do, this is just a class with a little bit of data, but one of the things that I have done is I have created a factory method for actually instantiating the to-do. It's a private constructor that's called from this method. And here I perform a lot of validations. For example, a to-do should have a name, or otherwise we get an exception, etc., etc. This kind of thing, and I don't think anyone will be surprised, are great candidates for testing with unit tests. And as you can see, the tests are very simple and very repetitive, and so it's very easy to fixate the implementation of these requirements. Where it gets a little bit more interesting is how do I test the implementation of my repository? Because for the implementation of that repository, I actually have to cross a boundary into another component, being CosmosDB. And what I want to do is I want to kind of write these same simple tests as I did for unit tests. I want to instantiate a to-do, and then I want to add it to the repository, and I want to see if I can get it again. And then I want to verify if it's the same thing. But for this test to run, it needs to have a CosmosDB with a database, with a collection, where it can store those to-dos and retrieve it again. Now, what I find important here is that I do not interfere with any other system. So really, I want to at the least have a new container for every individual test. And to make this happen, I write a class that I call a test context. In this case, a Cosmos test context. And this is a class that I write myself, and it has two important methods that I call from my test class. First of all, I call setup. Well, actually, I shouldn't lie, there are three. I set up. This method is used to do all kinds of initialization that I need. And then on my context, I want to get a configuration that is ready to be used by the repository. So my context should be able to provide a database, a locator, a password, and a collection name to the test for execution. The third method is, of course, that after my test has run, everything should be cleaned up again, because nobody wants to pay for thousands and thousands of CosmosDB collections that are no longer used. Diving into that context, what this does, it gets an existing Cosmos database, and within that database, it creates a new container. And when the configuration is requested, it returns those 4 values. And once done, it removes the container again. So here I have done what I described earlier. I create a bit of a namespace or container or scope for the execution of my test in a production system, and I clean it up after the test. And I think these kind of integration tests are most representative for the real world. Now, I also have a part of a system that writes messages to a queue. And here I can do completely the same thing. This is the class that sends messages to the queue. And if you look really closely at this class, it is nothing more than a small wrapper around the NuGet package for writing to a queue. It only handles the serialization and nothing else. Now, if I want to test this implementation, I have to write this. I have written another queue test context. It again has the same 3 methods. Initialization, give me the configuration that I can use for testing against queues, and tear everything down after the test. And then once that is in place, this is my test. I create a to-do. Here I start listening to the queue. So this will pause my test later on until I have received the message. And then I send the message to the queue. And here I do the actual waiting. And again, I have created this queue just for this single test, and I will remove it again after the test. That's how I implement integration tests. Now, finally, there are system tests. These tests are designed for running against an already deployed system. So here, I do not have a test context because I don't have to run against this separate container. And what I do here, there are a lot of techniques for writing system tests. You can use things like Telerik, test runners, or you can use Postman, automated test execution. But I tend to just write them in C# because I know how to write C#. And that means that I can execute them from my local machine, just like any type of other test. And I just instantiate an HTTP client, create a to-do, DTO, and then I really call into the location of the system. Of course, this location should be parameterized, but for the sake of readability, I've added it here. I wait and see if I get a response status code. And once that is done, I'm just going to go and directly connect to the database. And I'm going to see if that to-do has been saved. And here I have tested a complete flow from my system, accepting a message, to putting it in another system, being the database. These are 3 examples of unit integration system tests. So let's try to pick up the PowerPoint slides again. Moving on. So what we've seen so far is that testing distributed systems is hard because they have these integration points everywhere. And we kind of want to write automated tests for the component as a whole. But one of the things that we also have to think about is those that believe in manual testing. There are going to be people that say things like this. We need to verify that our system integrates correctly with all the systems we depend upon and all the systems that depend upon us. There is, by the way, now a question coming in, why not apply contract testing? I think, which is a very good question. So let's see if we can maybe touch upon that topic in a bit. What happened when we started moving to production is that people were very uncomfortable with us not testing our system against all other systems that we were going to interact with within the production environment. And they said to us, we should connect your test environment with our test environment. And my answer was quite blunt, because I don't think that was a good idea. Because the problem is that this line of reasoning will not stop before all the test environments in the whole company are connected. Because my system needs 2 systems, and one of those systems needs another system. and to have a really, what we call in Dutch, a ketentest, and I apologize, I don't know the English word, will very quickly end up with everything being connected. And the consequence of this is that other people now rely on my test environment to perform their tests, just as I rely on their test environments. And all of a sudden, people will start getting complaints when their test environment is down, because other people cannot move ahead. Now, I don't know about your test environments, but my test environments are down sometimes, because that's why it is a test environment. I don't want to give an SLA on my test environment. So I don't think that this is a really good idea. And another problem that you get from running tests in a connected environment is that sometimes tests will fail, and they will leave state inconsistencies between systems. Let's say we have an approach to setting up user accounts in 3 systems, and the provisioning fails in 1 out of 3 systems. And then we reinitiate that, and it fails because the account already exists, which is valid, but in the 3rd system, it will never come up. And then another test case comes up where we need that user to pre-exist, and that test case will fail. And then the tester will say, yeah, we already knew that this was going to fail, so we're just going to ignore this negative test. And that problem will grow and grow over time. So, and if you want to remediate that, you're going to have to spend a lot of time and energy on keeping all those test environments in sync. So I try to not do this. That fight we won. And then the question came, should we connect all acceptance environments? Which was a very funny question, because we didn't have an acceptance environment. We only had test in production, and we did all our tests. And actually, one of the speakers comes in and says, a Kten test is a chain test. Thanks, Gerald. So the question comes up, should we do a chain test on our acceptance environment? And again, me being me, I thought that wasn't a good idea, for the same reasons actually as for the test environment, but also for another reason. And that reason is that once we want to go, in the acceptance environment, we are running 4.86, and the system that we're calling is running 0.32. And we both have other versions in production, which is actually very normal, because after you've deployed, you start working on your next version. Now, when we want to deploy to production, all the test results in our acceptance environment are actually becoming invalid, because we have verified that our 486 can work with their 32. But actually in production, we're going to work with their 30. So we only know if our product or our component is going to work with their future versions and not with their actual versions in production. So I think another reason against all kinds of connected pre-production environments. But then the question comes up, where should we do our final acceptance testing? Production maybe? East-West, production best? Sounds dangerous, and I think another controversial statement. So let's reason about how weird or how dangerous that really is, and see if we can find techniques to improve upon this. First of all, there's a technique called feature toggles, and we can use feature toggles to remove an old idea about how we write software. And that idea is that once we have a new version, we build it and we deploy that new version onto our servers. But what if we let go of that idea, and instead of making a change to something, we copy something and we make the change only to the copy. And then we deploy both of them in parallel to production, and at runtime we decide which path to take. That's feature toggles. We deploy both the old and the new code into production, and we open up the new implementation first only to our internal users or our testers. And only once they are satisfied, we slowly open up the feature to more and more users. Now, of course, this sounds very risky, but remember, this is under the assumption that we have already unit tested, integration tested, and system tested everything before we get here. So this is not me saying just write something and throw it into production. This is about very, very carefully releasing something into production, because I have accepted that it's very difficult, if not impossible, to predict how something will behave in production from non-production environments. Now, another thing that we can do is, instead of feature toggles, is using experiments in production. Because looking at this OR in the implementation, what happens if we replace that with an AND? What if we run both the new and the current implementation of an algorithm in parallel, compare the results, and if they differ, we write it to our logs so we can follow it up for fixing, and always return the result of the old implementation. Just a random thought, but we call this running experiments in production. And I've written an example of this using a package called Scientist. It's a ready-to-go NuGet.org package. And I have used this to write 2 implementations of the Fibonacci series calculator. As you know, for Fibonacci is defined as adding numbers. And if you do it in a naive way, it will become imperformant very quickly. So there are other more complicated implementations that should produce the same result. And what I wanted to verify was if that more difficult, more elaborate implementation was working correctly before I released it. So whenever a Fibonacci request came in, I just ran them both in parallel. And if there was a difference, I wrote it to the logs so that I can fix my new implementation. And after a while, I can just take the old one out. Now, another thing that we can do is contract testing. Because a lot of the problems in distributed systems come up when we are expecting something of another, and we are not really sure if it's going to uphold. So what we can also do is contract testing. And what that means is that both the producer and consumer of messages or calls or communication agree upon how we should interact with each other. And both pre-production and production, we constantly validate that all the messages we are sending and receiving confirm to that agreed contact. And if we find a message that doesn't comply, we're just going to decline it. That means that if I have an abstraction for interacting with the queue, which is very thin, so I can have very, very limited integration testing, I'm just going to add one more thing, and that is the message validator, just before I send the message. And this is to catch cases like there is an unchecked input where somebody can put in a name of 25,000 characters while that doesn't comply with the contract with my downstream consumer. Instead of bothering him with it, I can now find this error myself and maybe do some graceful handling before I terminate this call. Same thing the receiver of messages can do. Every message that comes in, instead of just directly trying to process them, the other system is first going to validate if that message complies with the contract. And only when it does, it's going to comply it. So both parties independently of each other constantly validate each other's and their own messages. Of course, that is only very, very useful if we have a shared description of the messages that we're going to validate against. So for example, something like JSON schema, Avro schema, but it can even be a DLL that we're both going to invoke to validate messages. At least as long as it is something that we can both use to validate the messages. So now we have done everything we can to prevent error, but still error will be there. So let's see how we can monitor what's going on in distributed systems and improve upon that. Now, first of all, we have to do all the things that we also already did for non-distributed systems, and we need to do them for every individual component. We have to alert on every backend invocation. We need to have dead letter queues everywhere. We need to alert whenever a message is on the dead letter queue. We can't just leave them be there and don't take any action. We need to alert on resource consumption limits, especially if you have many, many components. There might be more constraint in the amount of resources they can consume. So we have to keep tabs on everything to see if things are not stalling. And whenever critical log entries or failures come in, we need to be alerted to them so that we can take action. And of course, with all these alerts coming in from many, many components now, not just one system, we really need to make sure that we remove all the noise from the alerting, because otherwise people will get tired of these alerts very, very quickly. Another thing I think that's really unique to building distributed systems is that we have distributed tracing in place. If we have 20 components, we cannot have 20 log stores with all the log entries only to that one component. Because we have already done rigorous testing, it is very likely that when any error occurs, it is due to the nature of being a distributed system. So whenever we call another system, we should send some kind of identifier along with that request that every component uses and passes along so that we can correlate logs that span multiple systems. And the second thing I think that we should consider is using synthetic users. So we're going to use a tool or something that we already know to emulate the behavior of a user towards the completely distributed system. And given time, I'm going to show you the second one. Now, there are a lot of ways that you can implement synthetic users. You can use them, instantiate them using application insights. You can instantiate many of them using load testers. But if you're already using C#, it doesn't have to be very difficult to implement a synthetic user. In this application, I have also included a very simple Azure Functions plan. And my synthetic user is implemented by just creating a post to my API, executing that post, making sure it was a success, and retrieving the identifier from the to-do that I just posted and that was created. And for a while, I'm just going to wait and repeat. And then I'm going to call in another component to another component. So this is an external part. I'm going to call into an external part to verify if that to-do has been saved there as well. So I am going to follow the flow along through all systems. I'm going to verify if it has correctly arrived at the end. And I do that just in an Azure function because I already use functions, and I can just do something like this. I can monitor if the function executes every 5 minutes correctly. Now, where Stacey had a lot of problems in the preparation and then everything went fine when presenting, I had no problems when preparing, but when running this actually this morning, everything started failing. But I hope the purpose of this function is very clear. Every 5 minutes, this function emulates a user and an end-to-end user flow. And if this function starts failing, I will get notified, and I know that even though, well, maybe all my components are up and running, still the user experience is not working correctly. So it's the final thing that I wanted to share, and also that you really don't need fancy or expensive tools to implement a few synthetic user scenarios. Of course, if you're going to implement many of them, you might start looking at tools. Alrighty, so what are our takeaways? First of all, don't start building distributed systems or microservices where you don't have to. Taking that off repeat, what I've learned was, don't try to connect your non-production environments with other components. It is a story that will not end. It is a story that will take you a lot of time. Build a proper pyramid of tests for your systems. This is even more important when you're responsible for a single component in a larger whole. Provide a means for integration testing to your consumers. If you are writing integration tests, it is great that you can get a testing scope in their environment for your tests, so please be kind to others and do the same for them as well. Consider contract testing. It's a valuable tool for identifying errors and problems when they are being created, and not only have the downstream problems later on. Monitor every component at the individual level, implement distributed tracing, and also add synthetic users whenever you can. Right, that's it for me. Please do try this at home. If there are any questions, feel free to launch them, because I will be here, I think, for close to 10 minutes answering questions. So thank you.
Thank you, Henry.
And let me save you from this animation.
And welcome back at our studio. We have one pending question by Menno Jongerius, but it's in the YouTube chat. I don't know if you have that YouTube chat open because I don't really understand the exact question. And for me, we also have a couple of questions for you. And the first one is about developing distributed systems. Would you say it's a good idea to always start developing distributed systems right away?
As opposed to starting as a monolith?
Yes.
Well, I think only a CF deals in absolutes. And I think always is an absolute. I think distributed systems or microservices are a solution for specific problems. And if you don't have those problems, why are you building microservices? And I think there is a pattern. I cannot get the name, and I apologize for that, but I know that the article is written by Martin Fowler. And it's quite a few years old already. And his argumentation was all the excellent microservices implementations that we're seeing right now are broken up monoliths. Mm-hmm. Because if you have built a monolith, you have a very good understanding of what your system is, what problems you are solving, and it's much easier to find the right boundaries between services. If you start out right from scratch with a microservice and you find out that you have drawn some of the lines wrong, it might take a lot of work to repair that after the fact. And often it is easier to repair things within a monolith and then split things off whenever necessary.
Right, that makes sense. I see that Menno responded. He says how to handle business wanting to try functionality that makes irrefutable changes to the environment. So
the business wants to try something after which there is no going back.
Yeah, that's how I understand it.
Yes, then I think it is time to educate him on the laws of physics. It's a discussion that I've had a number of times with people around me. So at some point, things they are asking are not possible. We can do a lot, but if it's not possible, it's not possible. But there are things we can go a long way to make things possible. Let me give an example. Let's say that we want to experiment with a change into our database schema, and we write a very long SQL script that transforms our current database schema into the new schema, taking all data along, but we don't know if we can go back safely. What we can do is we can write our code in such a way that it can execute all queries against both the old and the new schema. Mm-hmm. And the writes we execute against both, and we really commit them. The reads we write against both as well. We always return the result from the old database system, and we just compare the two. So basically, we're running an experiment.
Sounds a little bit like A/B testing.
Yes, but we can't go so far to really duplicate the whole database system. That's the point where I wanted to go. Mm-hmm. And I know there are parties in the world doing this when they want to make a risky database schema change. Mm-hmm. And apparently, so Menno said, I am reversing irreversible and irrefutable. And his environment is also pushing for an acceptance environment. But the reason you don't want an acceptance environment is probably because more environments is more work, is more time taking you away from making changes to the production environment. I think the question there to ask the business is, what is the value that the acceptance environment will bring in their eyes, and see if you can find another or better way to find that value from your test environment or from your production environment. Do I have to wrap up?
No, I think we have one final question by Tom Brink. He came in over Twitter. So the question is, why aren't you using HTTP test client for your system tests?
HTTP test client for my system. That's a very good question. I'm not familiar with the thing. So, but one of the reasons that I can think of is that you're going to make changes in the system. Mm-hmm. And to some extent, they will invalidate the outcomes. But as I already admitted, when making outgoing HTTP calls from my system, I cheated there as well. So I think you're probably just pointed me to a tool that will make it easier to do what I already did.
Yeah, so please, Tom, if you have any good tips, share them on Twitter. I think what he's asking for is a thing that we already implemented together as a team, but then you left and you probably forgot. I don't know about that. So do you have any question for the audience?
Yes. And you gave me plenty of time to think of a question, but I found it actually very... So what I came up with is, dear listeners, what is a common reason for developing distributed systems or microservices architectures? And I think the goal is that you tweet the answer using the while following 4.net and using the hashtag 4.netconf.
Exactly.
Nice.
That's awesome. Thanks for the heads up. And I also see a copy of your book in the background with your nice Lego project. Maybe you want to show that to the audience so that they're familiar with the cover if in case they want to buy it.
You're really putting me on the spot here. Probably say no. That's not an option. Sure. So yeah, here it is. Implementing Azure DevOps Solutions. Written not only by me, by the way, but also by Mike van der Graag, who has provided his insights both as a reviewer of the first half, and he has written the chapter on containers. And if you're into books, I am working on a second book. I'm not going to spill any beans on that one. So stay tuned. Bum, 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 bum.
Ooh, interesting. So, all right. Thanks for now. I think that's it. We were really, you were a really pleasant speaker. We love you.
Thanks. Well, thank you for the invitation.
So for everyone watching the stream, buy that book because there's a lot of valuable knowledge in it. And I guess we will probably speak each other at a later stage. And then it's time for us to wrap up Henry's talk and move a little bit back to Stacy's talk, because Stacy also had a question.
And her question was answered correctly by Jirai Cabello. I don't know if I pronounced that name correctly, but Jirai Cabello, you're one of the guys who tweeted the correct answer, and you're the winner of this awesome power bank provided by Microsoft. So congratulations there.